In this video, I want to go through the intuition of how you might solve question 2. Again, remember that I'm not here to just give you the answers, but to empower you to solve them for yourself. So, the problem that we're dealing with here is a traffic congestion problem. We're asked, given the information that an average of 2 cars arrive every minute, that their arrivals are independent, and that the arrivals are identically distributed. If we have more than 20 cars arriving within 10 minutes, we report a congestion. What is the probability that a congestion will occur? And so the first question is, what kind of model should we use? What kind of probability distribution should we use to model this issue? And I'll pull this up because this is a giveaway to what the model we should be using, but the model that we should be using is the Poisson distribution. The Poisson distribution. And the reason for that is because the Poisson distribution is a discrete probability distribution, meaning it takes on specific values. And it is appropriate for modeling the number of events, for example, the number of cars arriving, that happen over some fixed period of time. And we're told that we have a snapshot of time, a fixed period of time, and that we're told that we have a constant arrival rate. So that satisfies the conditions to use the Poisson distribution. So that's the first hint to this problem. The first hint to this problem is use Poisson distribution. And actually, even further, I recommend reading through this and citing it because I think it's incredibly useful. It's available on my Canvas. So the first hint is use the Poisson distribution. Okay, so what's the second bit of intuition? Well, let's look at the Poisson distribution. It has the following form as per his document. The probability that the Poisson distributed random variable x equals some number of occurrences k is given by this. And so this lambda variable is the average number of occurrences, the rate parameter. The k is the number of occurrences, and then everything else here, the constant. This exclamation mark is k factorial. So what that means, k factorial, what that equals is, k times k minus 1 times k minus 2 times k minus 3, so on until times 3 times 2 times 1. That's what k factorial, that's what the denominator here represents. So what I'm going to do is I'm just going to borrow this probability mass function. I'm going to toss it into Paint here, just so we can work off of it. So we need our rate parameter here to determine the probability that our Poisson distributed variable equals some value that we're after. We need to know what is this. What is lambda equal? What does that equal? And for us, lambda is the average number of occurrences in an interval. So we're told we have an average of 2 cars per minute. So 2 cars per minute, or 2 simply, would be our lambda if we're looking at arrivals per minute. And in this case, the number of cars arriving would be our k value. That's the number of cars arriving. And if we're using a rate parameter of 2, that's the number of cars arriving every 2. That's the number of cars arriving if we assume that there's an average of 2 cars arriving per minute. If we go back to the document quickly, we'll see that the mean and variance are both equal to the rate parameter. And this means that the expected value is equal to the rate parameter. And that's the second hint there, is what is our expected value for the number of cars arriving. Right now we have this rate parameter per minute, and we need it to be expressed over 10 minutes. So what could we do to convert something that's per minute to 10 minutes? I'll leave that with you, but I think the answer might be obvious. The third hint I'll give is, it's also in the document here, there's a property that Poisson distributions have, where let's say we have multiple Poisson distributed variables. And let's say, just to make things easier, and I'll clear this out here. Let's say that we had two variables that are Poisson distributed, and one had a rate parameter of 5, and the other had a rate parameter of, let's say, 7 occurrences, average occurrences, for that whatever interval they're in. Then if we took the total, the sum of these, they would also be Poisson distributed, and the rate parameter of that combination would be the individual rate parameters added together. So in that case, it would be 5 from the first one plus 7 from the second one, or 12. And that would be the overall rate parameter for the new one that's formed by combining the new Poisson distributed random variable that's formed by combining these two existing ones. And so what that leads us to is a pretty key conclusion, which is this. If every minute has the rate parameter equal to 2, and there's 10 minutes, and each of the arrivals are independent and identically distributed, which you'll sometimes see written as IID, then we should expect the overall distribution over the 10 minutes to have a rate parameter of 2 plus 2 plus 2 plus 2, so on, 10 times, or in other words, 20. 20 should be the rate parameter of the overall distribution over the 10 minutes. And so that's a huge hint for how you should solve this problem. Now, what's the condition again that we're solving here? The condition, just to remind you, is given to us in the question right here. If more than 20 cars arrive within 10 minutes, we need to report a congestion. So that's the condition. The condition is this. The condition is, or another way of thinking about it, is an event. The event that more than 20 cars arrive within 10 minutes. That is what we're after. We're interested in determining what is the probability of this event happening. That's what we want to determine through the process of doing the simulation. A couple more hints I'll give you. The next hint is this. If we have the probability that we want to find the probability that x is bigger than 5, for example. And what I'm saying here is we want to find the probability that a Poisson random variable is greater than 5. That's equivalent by probability rules to 1 minus the probability that that random variable is less than or equal to that same value 5. And this probability right here is really straightforward to find with a computer, And that probability there has a special name, and or that probability is obtained from a special place called a cumulative distribution function, which is CDF for short. This probability is obtained from a cumulative distribution function. This probability that a value is less than the probability that a random variable is less than or equal to a value. More formally, just to be succinct about this, a cumulative distribution function, a CDF, is defined as a function that tells us the probability that some randomly distributed value that follows some probability distribution, so there's a different one for Poisson and for binomial and for Bernoulli and for normal and so on. It gives us the probability that the value is less than or equal to some value. So it tells us the probability for that distribution to be less than or equal to some value. And in R, there's a bunch of functions, especially for Poisson, that lets us calculate exactly what this is. And so let me briefly pause and open up RStudio so we can show you this. Okay, so I'm back in RStudio here. And what I want to do is to show you the Poisson version in R, the Poisson version of the cumulative distribution function, which is called PPOIS, short for probability of Poisson. It's written like this, PPOIS. And PPOIS, it takes the value as arguments. This function takes the value we want to search as the first argument, the rate parameter, lambda, as the second argument, and then the third argument is called lower tail. By default, this is going to be true, and I recommend leaving it true. What that third argument will do is give us a cumulative probability. If you change it, it won't give you the cumulative probability. So let's say this is the task. Find for a Poisson random variable probability that it is greater than 5. And in R, the way we would do that is say this. PPOIS, the value that we want to search for, which is 5, let's assume that rate parameter lambda is 2, and then we'll explicitly say that the third argument is true. And have a look when I run this. I get a probability value here of 0.983. So this is the probability of less or equal 5, and save that to a object. And then so probability greater 5 then would simply be 1 minus that by the rule that we just established. And if we have a look, run this, probability greater 5, we get 0.0165. And that's how we can use the PPOIS function to do cumulative distribution functions inside of R. The next thing I want to show you is randomly generating numbers that follow the Poisson distribution in R, because we can't do RUNIF anymore, and the reason for that is because this is random uniform distribution, which we are not dealing with a uniform distribution, we're dealing with a Poisson distribution. So we need a similar function, and maybe you can determine what the name would be. But the function that we need is called RPOIS, short for R random Poisson. And this will let us get random numbers from a Poisson distribution. And the arguments of RPOIS are the number of values we want to get, let's call that n, and then our lambda, our rate parameter that we specify. And so again, let's go back to RStudio, and let's do this. And let me actually, rather than delete that, let me just comment it out. So, task 2. Randomly generate 10 numbers from a Poisson distribution where lambda equals 2. And so what will happen here is we'll get that many random variables that we're after, whatever, 10 in this case. We get, not random variables, sorry, 10 random numbers that are following a Poisson distribution that has a rate parameter that we set, and it's going to be very close to or centered about that rate parameter. And so the way we do that is our POIS 10, 2. Run that. And there are our values, 10 of them following the Poisson distribution with that rate parameter, that lambda value of 2. And we can, of course, assign this to a value, assign this to an object so that we can work with it later on. One important thing I'll mention here is the function called setSeed. So it's written like this, setSeed, and then we put in an argument of a seed number, a value. What this is going to do, simply put, is it's going to make our random number generation repeatable. It's going to let us, if we do random number generation, get the same random numbers every time if we're using a seed. So let me show you. I'll set a seed of 111222 right here. And then I'll do our POIS 10, 2. And very quickly, let's just run this line and then this line. So if we have a look at our output, we have 1, 4, 3, 1, 4, so on. If I run this line again and then run this line again, I get the exact same output. Watch what happens though if I were to uncomment this line and then run it again. I would get 3, 3, 1, 2, whatever, and then 3, 2, 2, 4, and then 2, 2, 2, 3. So I get much different numbers, but when I set seed, I get the same random numbers all the time, and this is going to be incredibly necessary for you to do on the assignment in order for the professor to be able to assess if you did the right things, if you calculated the right values. Because if we're generating random values and we don't specify which ones, you might get some random values that work for you but don't work for him, and that can create a lot of confusion. So, with all that said, let's summarize briefly. How should we solve this problem now that we have all of this kind of intuition on how to approach it? There's a couple steps. The first step, and I'll write them down as a sort of checklist. The first step is this. Set a seed value, and this is based on your student number. So let's say your student number is 00044455555, then you would do this. You would write set.seed 00044455555, and that's just to make sure that we get consistent random numbers. Next, what we're going to do is create a function to do this task. And this function should have an argument that tells it, that defines the number of Monte Carlo simulations to do. So we could write something like could write something like, I don't know, congestion calc is function trials equals 1e to the 6. And then, have our function body here. The next step would be, and what I would recommend is use a loop, whatever loop you'd like, simulate pulling out, or taking one random value at a time from a Poisson distributed Poisson distribution using RPoise, like we just learned earlier. This will give us a random number of car arrivals centered about the lambda that you specify in RPoise. Okay, so that's the third step. The fourth step, now we branch into two cases. So what are these cases? For A, the case would be simulate the first case of the total number of cars arriving in 10 minutes. And then use that to find the probability of congestion. And we could say that probability would be the number of congestion outcomes divided by the number of Monte Carlo simulations that you did. And then the alternative option would be, or the second branch that we have to do, is simulate the number of car arrivals for each minute of the consecutive 10 minutes and use that to find the probability of congestion in a very similar way. And then our final step would be to compare 4A and 4B. And based on our theory from our professor, these two answers, 4A and 4B, should be similar. They should be very close. And the idea here would be to discuss how similar they are. What are their differences? If there are ones, why do you think there might be differences, and things of that nature. But this is how you would approach question number 2 for this assignment.